Salah Mohammed from Southern Illinois. He's speaking about the Vargas equation with affine noise.
Good word of thanks for the Institute for inviting me here and for this pleasurable company. Yeah, appreciate that. Okay, I want to look at the Berger's equation with affine noise. I mean linear, it's multiplicative noise. It's a linear. Oh, it's not on? Oh, yes, thank you. Thank you. So it's start again. Berger's equation with affine noise. That means you have multiplicative noise that will have a constant part, constant variance, plus a linear part. Okay, we are not able to do fully nonlinear multiplicative noise. Okay? And the other point I want to emphasize is that we would like, this is by the way, is a joint work with Tusheng Zhang, and we would like to emphasize the dynamical aspects of Berger's equation. So we're going to assume that everything is great. You have a stationary solution, not necessarily unique. Okay, we would like to study the behavior of the solution near the stationary point, stationary solution. Okay, so that's will be the point. And we'll be looking at topological effects near the stationary point, rather than looking for a solution or looking for an invariant measure. Okay, so keep in mind that we assume that everything exists. Okay, you have a stationary solution, except you have to work on the flow, and the flow is not very is not trivial. Okay, so I will start by a couple of acknowledgements. Tusheng Zhang, he was here from Manchester, he left, and research supported by the American NSF. Okay, so let me try to analyze the objectives. First of all, we would like to study the dynamics of Berger's equation on the unit interval. So it's a very simple case, and driven by affine linear multiplicative white noise. And then we will show that if you, instead of what you do, you solve the equation for each initial condition, each initial function, and you know there is a unique solution. But you would like to study the motion of all initial functions at the same time for each omega. Okay, so you're looking at the dynamics or the flow of the set of initial conditions. So typically you will get a flow in space L2, Hilbert space, infinite dimensional space. And in general, this is a hard problem to realize, because you are really looking at infinite dimensional state space, basically because there is really not any mechanism, machinery that's available. Kolmogorov's theorem, unfortunately, collapses in Hilbert space. So it just doesn't work. So there's no way of making a natural selection. You have to play this game with each example, class of examples on its own. Okay, the other thing is that we will show you how to compute the Lyapunov exponents. When you linearize, suppose you get this flow, you linearize the flow at the zero equilibrium or at the equilibrium. So I'm going to be a little bit more lax on whether there is affine noise, there is actually additive noise, or there is no additive noise. Okay, if there is no additive noise, you only have linear part, then you talk about zero equilibrium. If there is additive noise, then you might get a stationary solution, which is non-zero. But in any case, we will show that there is a discrete non-random Lyapunov spectrum. Okay, and the spectrum, of course, as you might expect, it will characterize asymptotics of the nonlinear flow near the equilibrium. So to tell you what happens near the equilibrium. Okay. Moreover, we're going to get sufficient conditions on the parameters of the Berger's equation for uniqueness of the stationary solution. So we'll give you some conditions that will say there is only one stationary solution. And sometimes also we can give conditions on the parameters that will guarantee hyperbolicity. Hyperbolicity is an issue that goes counter to ergodicity, in the sense that you might have some modes that the solution actually explodes, goes exponentially away from the stationary solution. So that's possible, and that's why we say hyperbolicity allows that situation. Okay, and more specifically, we will establish a local stable manifold theorem near the equilibrium in the hyperbolic case. So we will show that near the stationary solution, you can have two directions: one finite dimensional direction where the flow goes away exponentially, and one infinite dimensional direction, smooth direction, where the flow goes exponentially fast to the stationary solution. Okay, so this is a stable manifold theorem is a very basic result in finite dimensional dynamic systems. Okay, and so here we are basically establishing the analog of that in infinite dimensions. Now, if you have you don't have a linear drift, then we can say a little bit more. You can say we can construct a countable random family of local asymptotically flow invariant manifolds. So these are manifolds. That when we say manifold, we mean like C infinity manifold. They could be infinite dimension. In fact, they are infinite dimension, and they have finite codimension. So these manifolds have finite codimension I minus 1. If you're looking at the ith manifold, then its codimension is I minus 1. Okay, and each one of these invariant manifolds, the cocycle decays with fixed exponential speed, and this speed is determined by the Lyapunov exponent of the linearization. And it turns out that these exponents are actually fixed, so they are deterministic, because there is enough ergodicity in the Brownian motion that will give you this to be fixed. Okay, also in the absence of a linear drift, we will show that you have the flag, existence of a global. This is a global result, a global flow invariant random flag. So when you take this space here, and if you have ergodicity, if you have an ergodic stationary solution, then you can break this space up into layers. Okay, and these layers we call them a flag. So they are nested, and they cover the whole space, and each one of them is characterized by the Lyapunov spectrum exponent for that particular linearization. Okay, so let me go now to more details. So this is a summary of what I hope I can do in an hour, maybe not. Okay, so let me show you the master equation that we will look at. So here is the equation. So you can let me just every time we're going to refer to this equation. When you talk about Berger's equation, this basically would be the one that we reference. So here is the Laplacian part, the drift part, and this is a nonlinear Berger type thing. And this is what I mean. I said linear drift, so I put that in as a forcing possibility of forcing term. And here is this space-time noise, but remember that this is actually white in time and smooth in xi. So you can think of some much more general combination, like a sum of all these Fourier expansion of the noise. But the point is that there is no integration in the xi. Okay, we're only just doing differentiation. It's hard enough for this with the space time. Okay, and this is a linear drift. So that's why I call this affine. This term here, along with this is the affine noise. And all these are independent noises, are independent. Here you have, you see at the endpoints, you have zero boundary value problem here. And this is the initial condition. Okay, you are not tied up with this type of boundary conditions. You can think of periodic boundary conditions, and the theory basically works for that. More variations of this. Okay. Okay. So this is describing the coefficients here. These are constant coefficients. Just to make things work, you need this to be series converge, and you want this additive noise to be smooth in sufficiently smooth. I mean, I'm saying smooth, but if you have it smooth, it will work. But you might have C2 or something. It will make it work too. Okay, the WK are independent Brownian motions on a complete Wiener space, and the linear drift has a fixed parameter gamma, and the viscosity is nu, it's fixed, and the initial function is in L2. So L2 will be our state space. That's where we have the topology. The topology will be living in this Hilbert space. The manifolds and everything will be lying in this space here. Okay, and here I'm just saying that you can replace the additive noise term by space-time noise where t is white in t and smooth in x. So this is not this special format is not really restrictive. You can replace it by anything, by a series, a Fourier series. Okay, if you have the right smoothness conditions. Okay, all right. Here is an issue that's very important when you're looking at the dynamics in infinite dimensions, the issue of perfection. And that says that if you have a proposition P of omega, random family of propositions, you can basically make it work outside a set of full measure, which is invariant under the shift. The theta t, by the way, is a Brownian shift. So you want this set of full measure to be invariant under the continuous shift. And everything out inside this set will work. Every statement you make will be true for every omega in omega star. Okay, so it's a very strong condition. That means you can throw away one universal set of zero measure, and then everything works, including the shift that's there. Okay, so here is a major obstruction to analysis in infinite dimensions is the failure of Kolmogorov continuity theorem, basically because of the infinite dimensionality of the space. So this is known to collapse, and so you have to use different tricks in each example to make the right selection. There is no general. It would be nice if somebody can come up with an analog which works. Continuity theorem. Okay, so we know that the Berger SPD has a unique Miles solution, and you can look it up in Professor D'Aprato and Zapsh's green book. Okay, that's why written in green. Okay, so it has everything in there. Okay, so I just saying here, this is a shift, okay, the Wiener shift. You see what it does? It takes a Wiener path. Remember, omega is a space of Wiener path, and you just shift the omega so that it starts at 0. Okay, when s is 0, it starts 0. And now this is a nice shift because it's ergodic. It preserves the Wiener measure. It has all the nice properties. Okay, now here is a theorem. This is our first theorem. It says that if you look at Miles solutions of Berger's equation, then you can think of them like this. So u, the function of time, function of space, and function of chance. So you can think of them as a function of 3 variables. Okay, 3 variables, because you have perfection. You can do that, and they satisfy this co-cycle property. I think we heard about this the other day about the co-cycle. So this is essentially the same idea, and it's the closest thing you can get to idea of a semigroup. It's not a random semigroup, but it's the closest you can. Okay? And you see I write it here for all omega in omega because I'm assuming that you have perfection. So everything is okay. So this is the theorem that there is a co-cycle like this. Okay, for Berger's equation. And the other thing that, of course, is not so surprising because of the dissociativity in the system, if you fix t, the time t, positive t, and fix omega in that universal set, then you have a mapping from L2 into itself, and this mapping turns out to be compact. So it takes bounded sets into relatively compact sets. Okay, this is an important property, because this allows us to construct the Lyapunov spectrum. The compactness will give you the discreteness of the spectrum, and the ergodicity of theta will give you that the spectrum is deterministic. It's not stochastic. Then you can talk about hyperbolicity and all these issues, because you don't have to worry about which Lyapunov exponents are positive or for what omega they are. Okay, and more importantly, it turned out that you can develop estimates on the co-cycle and its Frechet derivative, because remember you have to linearize around the stationary solution. So you want to know the growth conditions on the Frechet derivative at the stationary point, and it is possible to do that, and we call this oscillatic type integrability estimates. So you can get them. These are kind of difficult to obtain because they are fairly technical to actually get the right the estimates which satisfy the oscillatic multiplicative ergodic theory. Okay, so as I said, this is a construction. I'll give you a little bit of idea about how to construct the co-cycle. Remember, Kolmogorov theorem doesn't work here, so we have to use some kind of ad hoc method, and here is one of these ad hoc methods. I will show you the how it works in the case where you don't have additive noise. If you have additive noise, you have to be a little bit more careful with a priori estimates, but it can be done. But it's a little bit more complicated because you have the linear noise and the additive noise together. So we'll pretend that there is no additive noise, okay, in this for this calculation that I'm going to show you, okay. But bear in mind that you can actually adjust it when sigma 0 is not 0. Okay. So first of all, what do? You take the linear part. This is basically the linear part of Berger's equation, and you look at the linear flow, or in fact, you just solve it. This is a one-dimensional. This is very easy, huh? It's one-dimensional.
So you said it's linear part of the Berger equation?
Well, yeah, these are the linear terms essentially. It's a Berger equation, except the u. Yeah, there's no. Huh? No, without the Laplacian. Just take the linear and throw away the Laplacian for the time being. Okay. Laplacian will come in a minute, okay? We should see it in a minute. So this is a nice equation you can solve explicitly. And in fact, here is a solution. This is basically our elementary calculus question. You just check it by Ito's formula. You'll find that satisfies the equation. And you can also read that the expectation of the, the infinite norm, Q, this one here, Q, is just a supremum. This is a supremum over time, over finite time of QT. Okay, so you can do that, and then you pretend that your solution of Berger's equation, again with this, is a product of something of bounded variation times the Q. So this is rough and this is a smooth. Okay, and by very simple calculation, you can show that the V satisfies also a random PDE, a Berger type random PDE. The difference here is that this Q here is the only random term that's showing up, and it preserves the whole, all the conditions are satisfied. Okay, all are satisfied. So the question now is, you solve this pathwise, but then you make sure that when you solve it pathwise, you can get all the regularity properties from the solution. Okay, from this equation 6. Okay. So just look at, just register this equation here. If you have additive noise, then you end up with a much more significantly more complicated equation, but you can still handle it. You can still develop the actual a priori estimates that will guarantee that you have a solution, and in fact you have a flow for all time.
Only additive noise.
What do you say?
If you have only additive noise, what noise is it then?
What noise? Additive noise, only you have, as I said, white in time and smooth in space.
Not white write in space?
No, we don't know how to do that.
You don't know.
I don't know, but maybe a good graduate student might know somehow. Okay. All right. Yes, sorry. Huh?
It's asking if you only have additive noise.
We have additive noise, yeah. Yeah, but the equation is not the same.
Why don't you include that in Q?
No, it's just going to be, no, I couldn't put it in Q. I wanted to show a simple case, okay? Yeah. It would just make the equation longer and you don't really gain any insight on what's going on. But this is doable. Yes, definitely. Yeah. Okay, so let's just look at this simple prototype case. And I said, I just want to show you a little bit beyond existence, because existence, you say if you fix f, then you have a unique solution that goes for all time. Now here I want to run the f at the same time I solve the equation. Okay, so I want to run the f and solve the equation at the same time. And it's nice that we can do this in one shot. We don't have to do it separately. Okay. So what do? We just rewrite it in the mild form. And remember, TT is a heat semigroup, the Laplacian, with zero boundary condition. So this is what TT is. Standard, we know everything about it. Okay, it's one-dimensional Laplacian. Okay, so let's first of all do local existence. Okay, we'll try to do local existence. So suppose you have a function, this is the initial function there. Then for some a, this could be random, by the way. It could be random. The random Berger equation, this is what I just showed you, has a unique local mild solution. Now this solution V goes from 0 to a into L2, and it is continuous. Okay. Now how do we do that? We say do a fixed point argument. So we fix some f0, some initial condition there, and then we define the space. This is where we're going to do the contraction. Basically, it is a contraction argument. Okay, so we do it there, and the Banach space of all continuous functions, and we give it the sup norm. So this is very standard Banach space, and we're going to use this notation here, Bf rho, also in the future, for any ball, closed ball of center f and radius rho in this space, in the Hilbert space. Okay. Okay, so we define this set now. Y. This is where I'm going to look for the fixed point, so to speak. See, those that not stay very far away from f0. Okay, for all t. And then we look at the mapping. Now here is the mapping. That's where you're going to do the contraction. So the mapping is goes from y into e, but it's also parameterized by the state space. Okay, a ball around the state space. So you think of it as a function of f and v, like this. You have v and you have f, and this turned out to be a very nice smooth map. Okay, and in fact, we can get a fixed point for this. Now, what is the fixed point here? The fixed point is that if you fix f, then you think of it as a fixed point in this second coordinate. Now, this second coordinate here is in y. Okay, and it takes you into e. In fact, it will go from y to y. In a minute, you'll see that if you make the contraction good enough, you can make it from y to y. And you still have this dependence on f, which is important for us because we want to read the smoothness of the cocycle from that dependence on f. Okay. Okay, so we say a fixed point is a mild solution. That's clear. Okay, you take a fixed point for every f, it's a mild solution. Okay, so how do we do it? We first of all we use estimates. These are standard estimates, heat kernel estimates in one dimension, very well known, and this one. So these are the estimates again. So they are very classical, nothing fancy here. Okay, it's just okay, and so we can adjust that a, and a is a time horizon, and rho 0 is a radius around the fixed in the ball, the radius of the ball. So you make this sufficiently small so that this becomes a mapping from y to y. Okay, and actually what you get is more than that. You get that it's a Frechet smooth, uniform contraction on y. So that means the contraction constant is uniform, and it's less than 1. Okay, and when you do that, then you can apply fixed point theorem. Fixed point theorem. And in fact, you can use what I call the uniform contraction principle, that there is A and rho 0 such that the random Berger equation has a unique local mild solution. Okay, so you get a solution. And remember, here I am emphasizing the dependence on F because I'm interested in seeing how the solution behaves with the change of the initial condition. So I keep track of that, and it turns out to be actually smooth. This comes from the uniform contraction. You have to go back to the contraction argument and massage it a little bit to see that it also generates smoothness at the same time. So you get existence and smoothness in the initial condition by one go. Okay? And it turns out to be fresh smooth in F. Okay, now A is random, of course, you notice that, and independent of the initial condition. So A here is random, this A is random, but it's important to mention that it's independent of the initial condition. Although it might depend on the center of the ball, but we don't worry about that too much. Because in a minute we will show that A is actually can be infinite, and you have it for all time. Okay, how do we go from the local to the global? The obvious way to go is to do some a priori estimates. Okay, so here is a priori estimate. Big V is a solution of the random Berger equation. So this is the big V there, and it's a function of all of them, and it's in C1 in T. And then for each omega, again, this is perfect statement. For each omega, this mapping is decreasing, which is very similar to what you see in the deterministic case. In the additive noise case, you have to work a little bit more because you have more terms to deal with, but you can still get a bound similar to this, although not quite the same. And you also have an estimate on the derivative, okay, or the gradient, so to speak, of the solution. Okay. So if you work with Berger equation, this should be familiar with this kind of. Okay, so now we go to global existence. The theorem says that for every F in L2, Berger's equation, this is the master equation that I started with, admits a unique pathwise solution. Okay, and you see the solution lies in there for each F and omega, for each omega and for each F. Okay. Such that the solution map, now here you have the solution map, think of it as a mapping in F in the middle and fix T and omega. So you fix T and you fix omega universally, and you get a nice map which is C infinity actually. C infinity means all Fresher derivatives are smooth. Fresher derivatives are smooth for all omega, perfectly in omega, for one universal set. Okay, and for all T positive. And they also map bounded sets into relatively compact sets. This is a diffutivity property. Okay, it's reflected in this statement. Okay, now how do you argue? Now the argument is very simple. Now you say, let us take the maximum A that we can afford, preserving all these conditions, including the smoothness and everything, and then from there on. You say this maximum cannot be finite, because if it were, you can start again there and extend beyond that, and you get a contradiction. So that's basically the argument. Okay? And the estimates, the a priori estimates will allow you to do that. To say that you can start, if tau turns out to be finite, you can start at tau because the estimates allow you to do that. And if you go beyond that, even in epsilon, you get a contradiction because tau is a maximum. So that's where the estimates come in. You see how I do it here? We have this. So you can take that limit exists because of the estimates. A priori estimate allow you to say that I can take T to tau as long as tau is finite. Okay, and so by local existence you can go beyond that, and therefore you can define extension from tau to epsilon there. Okay, and it turned out that, or you can easily check that theta 0 is a solution of the random Berger equation, but on a bigger, slightly bigger domain interval, time domain, and because this is maximal, you have to have this, okay? It cannot be. The important thing is that the tau here doesn't depend on the initial condition. Because if it did, then you would be in trouble. Huh? You couldn't say that the flow exists up to all time.
Your equation is kind of a sort of Burger's equation with this continuous function Q. Is it?
Yeah. But of course, you can add additive noise and still.
But
still.
in this way, so the difference is that instead of 1, you have Q.
Yes, yes, yes. So, but in any case, it turned out to be infinite. I mean, it lives for all time. Okay. Okay, and then you just translate to U, and that's very easy. You just multiply by Q, and you can read everything that is work for V, essentially will be for U, except the co-cycle property, because V, we'll see in a minute that you just have to play with it a little bit to get the co-cycle property. It's very easy from uniqueness. Huh? And the solution map, this is the original. You see, this U here is our Berger flow, okay, Berger stochastic flow, so to speak, okay. And so it is a very nice mapping, okay. C infinity in F, and it's true for all omega, and it takes bounded. And in fact, the Frechet derivatives, okay, it has bounded Frechet derivatives on bounded subsets of L2.
Probably it's even analytic.
It's even, I don't know whether it is or not, but for the oscillatic theorem, it's enough to have smoothness. I guess it might be nice. I don't really know. If it is analytic, then the manifolds will be analytic, which is nice. It's supposed to see infinity, but I don't know whether it is analytic or not. Maybe another problem for a graduate student.
We need a lot of graduate students.
Yeah, the question, I can't find enough of them in Carbondale. Huh? Okay, so here is the co-cycle. Okay, this is just a theorem about the co-cycle. Unique, so we call it the unique global Miles solution of Berger's SPDE. Take F in L2, and recall that theta again is a Brownian shift. Okay, in Wiener space. Then, if you think of U as a function of 3 variables, is jointly measurable in all 3 variables, and has the following properties. Here are the properties. The first property, of course, the co-cycle properties that I mentioned before, is C infinity, perfect. When I say perfect, I mean it is true actually for all omega, in omega, for all. And then I have the compacting property, dissipativity property, okay, U. And then I have the Frechet derivative. By the way, the compactness of the derivative, what time is this live? How much time?
Still, yeah,
Huh?
almost 30 minutes.
Huh?
Still 30 minutes.
Half an hour?
Yeah.
All right. Okay. The Frechet derivative is compact. This comes for free because the nonlinear mapping is compact. And if you take a nonlinear mapping that's compact, and C infinity or C1, you differentiate it, the Frechet derivative is compact. This is an important result because this allows us to say that the Lyapunov exponents are discrete. We have a discrete exponent because these are compact. Okay, and the mapping is strongly measurable. This one you need to apply the multiplicative ergodic theory requires this measurability question. Okay. Okay, and now here is this is probably the most important estimate here. It says that for each fixed rho and a, rho is the radius of the ball, and a is the time horizon. You have this estimate. These are well-known estimates, not well-known by name, but not in this case. It's called the oscillatic estimates. Okay, logarithmic estimates. And LK is a set of. This is the space of all continuous K multilinear mappings from L2 to L2. Okay, and this is given the K multilinear norm. So under all this notation here, you have this is finite. So this requires a lot of a good deal of work, estimates, yeah, and iterations and heat kernel estimates to actually get this get this result out. Okay, here is a nice picture. Maybe if you don't see many pictures in stochastic analysis. Huh? So here is the probability space, and here is the Hilbert space. You sample these green ones, Hilbert space. H is L2, huh? So H is just our L2, and we sample from omega like this, and then we look down here. You see the shift from 0 to T1, and from here you run the shift from T2, and you end up with theta T1 plus T2 because it's a group. The shift is a group, so you get this. Here is the cocycle. You take an F here, and if you can see that red, I don't know whether at the back you see that, but this is a red line here. It's very jagged. Okay, it's a random path, and it goes up to UT1, and then you start again UT2, and you run it, and you get UT1 plus T2 for every F and for every omega. So this is a pathwise in omega and in every F. Okay, so there is no distribution here. This is a really a random picture, but a pathwise picture. So this is a cocycle, and this is the dynamics. Basically, this is the dynamics. And I really advocate here at this point that in stochastic PDEs, this point of view is not emphasized enough. I don't understand why, but I think there is so much work to be done in this direction. But it's just a different field which attaches you to dynamic systems, which is not quite well developed anyway. Okay, so let's try to go a little bit for stability. I may have to go a little bit faster here to characterize the local behavior of the random flow of Berger's SPDE relative to a stationary. So now we have this dynamics. Now we say, let's take a stationary point. Okay. By the way, a stationary point is a point that's invariant under the cocycle, pathwise. So you have a random variable with values in H or in L2, and if you plug it into the cocycle, it reproduces that random variable. Okay. So this is a description of an invariant measure, but in a pathwise sense. And it fits in our status here because we can think of it as a random point running around in Hilbert space, and then we draw circuits around that point and then study how the cocycle approaches the stationary point. Okay, pathwise. Pathwise. Everything is perfect. Okay, pathwise. Okay. So now let me again, what I here, I'm going to assume that the additive noise is not there, but it can be true around the stationary function. If you put sigma 0, of course, equal to 0, then the only obvious stationary solution is 0. So you just fix it, okay, because you have a linear equation with 0. But as I said, you can modify every statement that I make by putting in a stationary point instead of 0, and you get it to be true. Okay. So what do? We linearize the equation at the stationary point. In this case, it's f equals 0. And when you do that, you get this. You get very simple. The linearization at the point is just Q, that Fudge factor, times the heat semigroup. So this is something that you can really analyze, and you know all the spectrum of this, okay, all the spectral theory of this. So that's very simple because we are looking at 0. If you're looking at a general stationary point, you will not be able to write it this way, but it's still compact, and you can still apply the oscillatic theory. But this is an example that we can all feel, and that's why I just say it around 0, okay, just for simplicity, not for generality. Okay, so when you write it out, then you know how to do that. We did that before. The Q, this is the Q, and this is the TP.
So you assume that the sum sigma k squared is finite.
Yes, this is one of the assumptions that I stated at the beginning. Sigma square is less than infinity.
So does it mean that actually you are doing with one-dimensional linear process?
Essentially. Because there is no, this is a good point that you mentioned. The sigma does not depend on the space. We don't know how to do that.
So if you take sigma k wk sum, it's just one-dimensional Brownian motion.
True, yeah. But that's I don't know how to do better than that.
But it is.
Yeah, it is, yeah. But I said I don't know how to make it more general. Yeah, I mean, as far as I'm concerned, if you can find something exciting, even on a special case, then it's still good. Okay, so TT, this is a heat semi group. Okay, we know it's a nice, it has nice spectral properties. And in this case, it turned out to be, this is not generally true, okay? In this case, it turned out to be self-adjoint because of the form. In general, it is not self-adjoint. So what you have to do is multiply it by this adjoint, Hilbert space adjoint, and take square root, or 1 over 2t, and let t go to infinity. So that will give you the oscillatic operator. Okay, now we know this discrete. You can write down everything about the Laplacian in 1 dimension. You know, Dirichlet Laplacian. Fn are the eigenspaces. You can write them down. It's very easy. Okay, now here is the theorem about the exponents, the Lyapunov exponents. Okay, this works also around any. It works in the additive noise case, okay, and around any stationary solution. So you can actually do that. So, but I'm stating it only for the linear case. And the reason is, of course, I don't. This is basically this is what we would do in general. If you are looking at a stationary point, you replace this 0 by a random point. Okay, you replace the 0 by a random point, and then you have to do this. Of course, because this is self-adjoint, it's not necessary to do that. And the Ruel oscillatic theorem tell you that this limit is discrete and fixed. Okay, it will tell you that this converges to an operator, a compact random operator, and it has discrete spectrum. In this case, because you are looking at 0, that's why I wanted to show you the 0, because you know these explicitly. They show up. The sigma k and the gamma, they actually show up. And you can tell whether they're positive or negative just by looking at that. And the limit exists in the operator norm. Okay. Okay, so the Ruel oscillatic operator, this is the one I just mentioned. This is called, by the way, this operator here, this is the limit. This limit is called the Ruel operator, oscillatic operator.
Can you remind what is T1?
T1? T1 is the semigroup at time 1, the heat semigroup. Okay, so now you say, okay, it's self-adjoint because you have multiplied by star, the adjoint with the operator, then it is self-adjoint. And therefore, you can take 1 over 2t, because it makes sense to, because it's a positive operator. You can take 1 over 2t, and then you let t go to infinity. And in the limiting operator, these are the spectrum of the limiting operator. Okay, because it's positive, you can write them like this, because these are positive. And you look at the powers. The powers here, the exponents, are what you call the Lyapunov exponents. And it turned out they'll be, in general, there will be infinitely many. Okay, because you are looking. Okay, so these are the Lyapunov. In this case, you can write them down explicitly because you are looking at a simple equilibrium. You can actually write down the exponents explicitly, like this. And they turn out to be also from the oscillatic theorem. These values here are the limits, almost sure limits of these logarithmic. See, here you take the log, you take the derivative of the co-cycle at the stationary point, and then you take the norm, the L2 norm, takes the log 1 over t infinity for any g. Remember, this is the fresh air derivative, so you have to evaluate at any g in L2, and this limit here will take one of these values. It can only take one of these finite values, fixed values, no matter what the choice of g is. Depending where the g is, you can pick up the right exponent. Okay, let me show you a little bit how to order these Lyapunov exponents. So you take E1 to be the whole space, and then En to be the orthogonal component. Remember, these are the eigenspaces of the Laplacian. And take the orthogonal complement of that and call it En. And then you notice that, of course, because all these eigenvalues are simple, the codimension of En is n minus 1. That's obvious. But this may not be true in the general stationary case. It's true in this case because we know exactly what these are. And so you have a nested flag. Turn out to be non-random. In general, this flag is random, but in this case it is fixed, turned out to be fixed. Okay. And the point here is that if you look at the Lyapunov exponent of the linearization, and if G lies between the flags, between say En and En plus 1 lies in between the two, then you pick up the exponent corresponding to that flag. So this is like lambda n. All right.
What you say? Why is the flag fixed?
The flag fixed in this case because when you do linearization around 0, it turned out that the oscillatic operator is a fixed operator. The oscillatic operator is a fixed operator. It's not random. But if you have a stationary solution, then it will be.
Okay, I understand. Yeah, got
Yeah.
it.
So in general, the EIs would be random.
Yeah, I understand. Thank you.
Definitely. Okay, and here is what people love to talk about is the top. They call it the top Lyapunov exponent. Here it is, the top Lyapunov exponent. Here, this is the operator norm, and you pick up the biggest exponent. This corresponds to n equal 1. This is the biggest exponent. So in some sense, if this is negative, then you have ergodicity. Okay, that means everything collapses to 0. Okay? And also you notice that the ENs are invariant, and this is always true. If you have a stationary solution here, it will leave this to be invariant. Okay, this flag, random flag. Okay, and here is, I hope you can see that the red usually doesn't show very well. I don't know, because of the background. Is it clear to you, this? People at the back? I don't know. Anyway, think of this as, this is squares here. For example, the one outside is the whole of the space, and then you have this nested E's, okay? One inside the other. And here is the derivative, linearization around the stationary point, or the fixed point. And if you start in between, then you end up in between. If you start, say, in the middle square, then you end up in the middle square. If you go from 0 to 0, from the stationary point to the stationary point, it's the same. Okay? So these are selections over the probability space here. Okay? Okay. Let me just show you. This is a concept I mentioned earlier on about invariant measure, so to speak, an invariant measure. We think of an invariant measure like this. Okay, mapping a random variable omega into the Hilbert space. Okay, mapping measurable. It could be anticipating. So this could be F measurable. It could be anticipating, and we call it a stationary random point or equilibrium if it is invariant under the flow. So if you plug it y omega, you reproduce y. That's what I said earlier on. How do you reproduce y? Up to the shift. And so the right hand side is a stationary process. Okay, under theta. So this is, and this statement here is perfect. It's for all omega. Okay, let me give you the stable manifold theorem. I think I'll try to do that around a stationary random point. So let's take a stationary random point. Let's assume this regularity on y, that the logarithm is integral. Okay, the log. So this is a fairly mild condition on y. And then you can conclude that the linearization is a compact linear cocycle, because remember from the existence theorem of the flow, we know that the derivatives are compact. So this is compact operator on H, and because of the integrability condition, which we proved earlier on, that is oscillatic integrability condition, and applying the oscillatic Ruel theorem, you can get that it has a spectrum. The spectrum here, I put lambdas, tilde on top, just to distinguish it from the one that's explicit that I explained before. Because here, remember, you are looking at around an arbitrary stationary point, not at 0. Okay, 0, that was an accident. We had just nice lambda. Okay, and now we develop this idea of hyperbolicity. We say that the the stationary point y or stationary solution y is hyperbolic if these are non-zero. Okay, if the lambda i's are not zero. Okay, and lambda 1, the top one, is positive. We insist that the top one is positive because we want to have an unstable direction, and we want to have a stable direction. Okay, so that's why. Okay, ergodicity of the zero equilibrium with no, again with, this time let's go back to zero equilibrium with no additive noise corresponds to, as I said before, that the top exponent is negative. Okay. In general, I would say this is a rather controversial statement here that I'm making here, controversial statement, because I say ergodicity is a non-generic property, but hyperbolicity is generic. And I'm saying this from the point of view of dynamical systems. If you look at dynamical systems in general, the systems that contract into one point are not, they are not dense in all dynamical systems. So you expect that if they have some level of hyperbolicity, you can perturb it. If you have any other non-hyperbolic system, you can approximate it by a hyperbolic system. Okay. All right. Okay. Let me. Maybe I should. This is. I will skip this. So this is easy to see that. I'm going to skip that one. Okay. I have 10 minutes or something. Is that okay? Okay. All right. Okay. So let us now. So I'm going to try to state now the stable manifold theory. Okay. What do we do? I'm going to state it for the zero equilibrium. Okay. But it's also true for the general stationary solution. Okay. So what do? You look at the Lyapunov exponents, and you look at the first one. I0 is the first one that becomes negative. Okay, you remember, so you have lambda 1, lambda 2, and they decrease like this, and then you stop, call it I0, where the first one becomes negative. Okay, and there will be finitely many of them until you get to that point. Okay. So the linearized co-cycle has invariant, stable, and unstable subspaces. So you can do that. Just divide the subspaces up to I0. And U and S, we call them U and S, are orthogonal, tend out to be orthogonal because they operate as self-adjoint, so orthogonal. And the dimension of U is I0 minus 1, the dimension of codimension of S is the same. Okay, so now we're going to assume that we have a hyperbolic regime, and again I define the same way. And now what I do, I look for epsilon 1 from 0. This is the negative of this, by the way. So this is going to be positive, and you take epsilon between 0 and that, because this is a negative. This is negative here, and therefore this is positive. Okay, take epsilon. And take epsilon 2 on this, just before, on the other exponent. And then the statement says this. There exists, this is a perfect statement. So omega star invariant under time. It's full measure. Okay, sure event. And we can get F measurable random variables, rho I and beta I, so that the following is true. There are C infinity. Now here is a, this is a stable manifold, okay, and this is an unstable manifold. They are random, okay, and they live near the stationary point. So if this is a stationary solution, then we put just y omega here, okay. But around 0, you get these manifolds, okay. This one turned out to be finite dimensional, and this one turned out to be finite codimension, okay. And they are transversal. They cross transversal, okay, at the stationary point, okay. Okay, now how do you characterize this one, the stable one? You just say, look at all F in the ball near the stationary solution, and look at how it grows exponentially. You find that it grows exponentially like this, okay, with this up to epsilon 1, which is a small perturbation, okay. This is on discrete, okay, on discrete. But on continuous, it's also true. So if you take the logarithm of the distance between u and 0, and let t go to infinity, so that you get this. For all f inside this stable manifold in the ball. Now the stable subspace S of the linearization is tangent to the submanifold S tilde. Okay, so you have the submanifold, the stable submanifold, and at the stationary point, the stable subspace is tangent. Okay, and in particular, the codimension of the stable manifold is I0 minus 1. Okay, depending on where you stop in the counting until you get hyperbolicity. And in fact, the Lipschitz constant on the stable manifold is dominated by the Lyapunov exponent of the Lipschitz constant is dominated by the Lyapunov exponent of the linearization. This is the Lipschitz constant of the nonlinear flow. Okay, so you can over, of course, this is local. All these results are local. Okay, there's no, we have some global results, but I probably won't have time to explain them. And then you have the invariance, co-cycle invariance of stable manifold. So if you take the co-cycle or the flow and you apply it to the stationary to the stable slice, infinity slice, it basically reproduces itself. It just says it takes it into theta tilde of it, just like the y omega is invariant under the co-cycle. So these manifolds also have the same property. And, and if you take the derivative, then the derivative preserves the tangent space to the manifold. Take the derivative, it preserves the tangent space. And you can do the same thing for the unstable case. It's a little tricky because these are compact and you have to back up in time, but it's possible to do that. You back up discretely. It might not be unique, but you can actually reverse the time. But you don't have, this y is not unique. There is one. And that's enough to define the unstable. And so you want it to look like this, because this is just the opposite, running the time backward, basically, essentially. And the point here is that you get these to be invariant under the co-cycle, and they also give you the Lyapunov exponents, running backward in time. And each unstable subspace U is tangent to U tilde, to the unstable. And that's why, because U is finite dimensional, that's why U tilde is finite dimensional. Okay? Although it might not be, the dimension might not be equal to I minus 1 like we said before, but it's finite dimension because the Laplacian, the operator is compact and has finite multiplicities. Okay, and in this case the dimension is I0 minus 1, non-random. Okay, and again you have the Lipschitz constant going backward in time is dominated by the Lyapunov exponent. Lipschitz constant on the unstable direction, and you have the invariance here. Is the invariance here? Again, as if you are running the time backward. Okay, T goes to this is the invariance, and of course also the linearization preserves U, and the restriction. Now this is different here because this says the restriction of the derivative to U is a linear homeomorphism onto. So this is actually a homeomorphism because this is finite dimension, the U. Okay, that's the reason. And again, the end you said the submanifolds are transversal. So if you take the tangent space to the stable manifold plus the tangent space of the stable manifold, they fill up the whole space. Okay, that's transversality. And as I said before, the local stable manifold still holds under hyperbolic station. Let me just finish by picture. I don't know whether you can see this one or not. So this is a sample of H, and here is the stationary point y omega, and it is transported into y theta t omega, and there is a ball around, a random ball, and then you see this is the stable direction, the linear stable direction. Here is the unstable direction, and this is the green one here is the unstable manifold, and this one here is the light green is the stable one. And if you start here, for example, you follow the flow, you end up here because it's invariant. Okay, and so you get that, and then down below here you have probability space. Okay. So basically what you have is you have y of omega, and you have a tube around it, and that tube is stationary. And then the cross sections of the tube, if you cut it, you see the stable and unstable. So that's a theory. I didn't have time to tell you about that, but there is a theorem about the random flag that you can actually globalize this picture, random flag picked up by the particular exponents. But that's maybe a longer story. Okay, thank you very much for your attention.
My question is concerning the perfect co-cycle property. You say that you allow additive type noise and linear multiplicative noise. Both are present in your equation at the same time. So I want to know which kind of transformation that you used in order to verify the co-cycle property.
It's a good question. I have to give you my preprint. It's a little technical. You have to, basically what you do it in piecemeal. You do the linear part first.
I mean, you do two types of transformation?
Yeah, and then the equation, the random equation becomes more complicated because they all pile up at the end. And then you have to do this a priori estimates to show that you can get a global solution. But I mean, if you sit long enough, you can figure it out. You see what I'm saying? But it's not, I mean, I tried it once or twice in one way, but I couldn't get the estimates. You see, the point is that you have to choose it in the right way, the transformation, so that the estimates also work. You see what I'm saying? Because sometimes you might do a transformation, but when you try to the Berger equation, the random Berger equation that comes out of it, may not be amenable to estimations. You see?
I mean, for additive type noise or linear multiplicative noise, they have a standard transformation.
Yeah. But when you have them together, you have to subtract one after the other. You see what I'm saying? Maybe you take off the space, the additive part first, and then do that. But I think the way we did it, we took the linear part first, and then we did the additive part. Okay. But it's not completely difficult, but it's kind of a little tedious, right?
Maybe a very stupid question, but I was wondering which Kolmogorov continuity theory you meant in the beginning.
This is the so-called continuity theorem. You know, when you have a infinite dimension, when you have a how do you call it, space-time noise, then you take the expectation of the difference, say at one point minus the other one, to some power, and take the expected value. If that somehow is like the distance between the 2 points, then Kolmogorov theorem says you can select a continuous version.
Yeah, but that's also true in infinite dimension.
It's completely wrong in infinite dimension.
No, it depends. I mean, in the topology of your dimensional space, you get a continuous version.
Well, it depends on the topology, yeah. We could take compact topology. Now, and I'll give you an example where this collapses. Take the following. So this is a very standard, not standard, but so take this in L2, okay? Like we are working on L2. Okay. Say into the real. So this is a random field, okay? For each F is deterministic. So this is a random Gaussian field, actually, okay? And it doesn't have. There is no way to think of this as so you could not make a selection, omega, that will work for all F in L2. And the reason is this satisfies, by the way, Kolmogorov condition. Because if you take the distance between, say, I of F1 minus I of F2, take it to square or take it to any other high power, the difference is, because of the isometry, is just the L2 norm, the difference of the L2 norm of F1 minus F2. So it satisfies Kolmogorov theorem, but it is not even bounded on small balls. This is actually goes to infinity on every ball. If you take every ball in F, this actually is unbounded, almost surely. And the reason is, why is that? You can see that very easily if you take this to be orthonormal. Suppose you take the Fn to be orthonormal, okay, in L2. Then these IFN are independent Gaussians. Okay, they are independent Gaussians. And so if you look at the supremum of this, that has, if you want this to be finite, this has probability 0, because you're looking at an infinite number, a countable number of Gaussian independent random variables, and if you take the probability of making them finite, it's 0. So there is no way you can say the I would be continuous, because on any ball it explodes.
Oh, with that I agree, but I mean, the usual Kolmogorov theorem is stated in an infinite dimensional setting, so it's a bit confusing if you say...
The one I know is finite dimension. Or there may be some
I can show you.
local compactness or something.
But you mean something else, that's clear.
Yeah. Oh, yeah, of course, yeah. If you can do it this way, then life will be good. Huh? Then you can do all SPDEs and get flows. Okay?
Other questions? Okay, so let's thank Sarah.